Hello, welcome all. Good morning. Let me first thank the organizers for giving me this opportunity to share my knowledge on spin resonance spectroscopy, especially NMR and ESR spectroscopy, their principles and their applications in chemistry, biochemistry. In this part of this lecture, I will give and explain the fundamentals of NMR, basics of NMR and EPR, comparison of NMR and EPR, how they are related, what are their applications in structure determination of simple, complex, protein, peptide, dynamics of these molecules. Before we start the lecture, in my PhD work, I prepared simple crystals of metal complexes and investigated using X-ray crystallography, powder single crystal EPR spectroscopy, IR UV visible spectroscopy, etc. I published around 6 papers in my PhD in molecular physics, Journal of Chemical Crystallography, Journal of Inclusion Phenomena, and Journal of Molecular Structure, etc. during my PhD. Thanks are due to my guide. I was immediately offered postdoctoral position in Medical College of Wisconsin in USA in biophysics department, which is part of Friedrich Hospital and Children's Hospital. This is the Medical College of Wisconsin. It also houses a National Biomedical EPR Center and a free radical research center where in this lab LDOR technique was developed. LDOR means electron double resonance technique. We have studied electron nuclear double resonance technique called LDOR in this lab department. LDOR technique was developed for the first time. I worked and carried out research studies in this lab as postdoc research scientist and also assistant professor briefly for more than 5 years. In this talk, it gives me pleasure to share my knowledge and research experience in India and in Medical College of Wisconsin. Based on my research knowledge and teaching experience, I have compiled all the aspects of NMR and EPR spectroscopy, including physical chemistry, organic chemistry, inorganic chemistry, and biochemical applications, and edited the book published by Elsevier entitled Spin Resonance Spectroscopy Principles and Applications. Spin resonance spectroscopy is broadly classified into two types, NMR and ESR. NMR deals with the nuclear spin resonance due to spinning motion of proton nuclei, either clockwise or anti-clockwise, like a spinning top. ESR deals with the electron spin resonance, similar to nuclear spin resonance. It can spin, the electron can spin either in clockwise or anti-clockwise. NMR was discovered by two American physicists, F. Bloch, Stanford University, and E.M. Purcell, Harvard University. They were jointly awarded Nobel Prize for Physics in the year 1952 for the invention of NMR. ESR was discovered by Russian physicist E. Zavoisky. It was discovered 1 year before the NMR. Before we see the principles, the fundamentals of NMR and ESR, let us see the important applications of NMR spectroscopy. NMR spectroscopy is a non-destructive analytical technique that is used to probe and characterize the molecular structure the types of atoms present in the sample. For example, carbon 13 is present, proton is present, phosphorus 15 is present, fluorine 19, and they are all NMR active. The relative amounts of atoms present in the molecule, how many CH proton or CH2 proton, the specific environments of atoms within a molecule. For example, it is acidic proton or NH proton or carbonyl proton, carbonyl carbon. The purity and the composition of the sample can be studied by using NMR. Structural information, stereochemical information, conformational isomerism, cis-trans isomerism could be studied by using the NMR technique. Let us see the important applications of NMR in biochemistry. For example, three-dimensional structural studies of protein ligand complexes, DNA, RNA, natural product chemistry, synthetic organic chemistry, study of dynamic process, reaction kinetics, study of equilibrium, and drug designing in neurochemistry, MRI, magnetic resonance imaging, metabolomics, what are the metabolites present in the blood or brain, etc. Now we'll see the applications of ESR spectroscopy. ESR is applicable only for paramagnetic compounds such as free radicals, transition metal ions, inner transition metal ions, etc. Simple inorganic compounds, for example, superoxide anion, nitric oxide, NO2 radical, short-lived intermediate radicals could be studied only by OH radical, H radical, fluorine radical in chemical kinetic study. What are the defects in crystals? What are the defects in crystal? Electrons trapped in radiation damaged sites. For example, gamma radiation will lead to electrons trapped in. So it could be used to study the radiation damage, radiation dosimetry, stable free radicals, and also unstable free radicals. By using spin trapping method, we'll see. EPR spectroscopy is also useful for studying triplet states, and also it has got lot of biological applications to study the iron sulfur active site, copper active site of various proteins, paramagnetic cofactors present in various proteins. For example, cytochrome C, it has got heme cofactor, and free radicals of biological origin and their spin trapping products. For example, tyrosyl radical, tryptophan radical, cysteine radical. There are several amino acid radicals are produced as well as protein radicals are produced. They could be studied only by ESR spectroscopy, and also spin labeling method we'll see, and also in radiation dosimetry. It has got several applications. Here I have given an outline of the EPR applications in various fields. For example, conducting materials, organic radicals produced in photosystems, in biological system, defects in solids like diamond. In diamond industry, it is used to study the defects in diamond. Excited states, for example, in photosystem, triplet states, and also EPR imaging, spin labeling, spin trapping in catalysis, nanocatalysis, etc. Let us now discuss the principles of NMR and ESR spectroscopy. What are the important properties of nuclei? What are the important characteristics of nuclei? Nuclei has mass, charge, and spin, nuclear spin. It can spin either in clockwise or it can spin in anti-clockwise. Due to this spinning motion, it develops it creates a magnetic field. Any spinning charged body will produce a magnetic field and a magnetic moment, as you have studied in basic physics. As a result of this, the nuclei are NMR active. NMR active. But we'll discuss later, not all the nuclei are NMR active. Only certain nuclei are NMR active. Why? We'll see now. Next slide. And next, ESR spectroscopy is exhibited by compounds with unpaired electrons and transition metal ions, inner transition metal ions or F block metal ions. While they were drinking beer and working in EPR instrument, they put the beer sample in NMR tube and they got nice peaks. Since then, chemists and biochemists use the NMR techniques for structural elucidation and other various applications. In this slide, we will see why only certain nuclei are NMR active. Not all the nuclei are NMR active. For example, carbon 12, oxygen 18, oxygen 16, they are all not NMR active because they don't have I value. The I nuclear spin quantum number is equal to 0. So, the nuclei which possess I greater than 0 are only NMR active. There are certain empirical rules which gives the relation between mass number and atomic number Z and the nuclear spin quantum number. For example, if the mass number is even and atomic number is even. For example, here in the case of carbon 12, mass number is even. As you see, mass number is 12 and atomic number is 6. It is also even. Therefore, I equal to 0. Similarly, for helium, the atomic number is even and 2. Mass number is 4. It is also even. Therefore, I equal to 0. Okay, now let us consider mass number is odd. For example, C13. C13 mass number is odd and atomic number is even. In that case, I equal to 1 by 2, 3 by 2, 5 by 2, etc. For mass number even, hydrogen 17, mass number 14, mass number is even and atomic number is odd, then I equal to 1, 2, 3, 4, etc. So, for nitrogen, I equal to 1. These are only empirical experimental rules to predict whether the nuclei are NMR active or not. These are all asked in common GATE or CIR examination. These questions are asked whether the nuclei is NMR active or not. It is not a theoretical rule, it is an empirical rule predicted based on the observations. In this, we will see what are nuclear quadrupole moments. Nuclei with I greater than half will possess nuclear quadrupole moments in addition to nuclear spin magnetic moments. Because of non-spherical distribution of charges in the nuclei, the NMR spectrum of these compounds will give broad absorption lines. Because of the interaction of nuclear quadrupole moments and nuclear spin magnetic moments. It also affects the line shape of neighborly nuclei. It is further dealt in separately in NQR spectroscopy. A nuclei with the nuclear magnetic moment nu because of the nuclear spinning motion, as we have seen earlier, when the nuclei is placed in the external magnetic field V0, there is an interaction between the nuclear magnetic moment and the applied magnetic field. As a result of the interaction of these interactions, the interaction energy is equal to minus mu cross B naught for NMR, for ESR E equal to minus mu cross B naught, where the nuclear magnetic moment is given by the expression Gn mu n I, where I is the nuclear spin quantum number. Similarly, for ESR, S is the electron spin quantum number, Gn is the nuclear G factor, mu n is the nuclear magneton, Ge is the Landé G factor, mu b is the Bohr magneton, where nuclear magneton mu n is equal to Eh by 4 pi mp. Mp is the mass of the proton and E is the charge on the proton. Similarly, for Bohr magneton, Eh by 4 pi me, where me is the mass of the electron, charge E is the charge on the electron, H is Planck's constant. Okay, now I can have values plus of or minus of, because of it can spin either in clockwise direction or in anti-clockwise direction. Similarly, for electron spin can also in clockwise or anti-clockwise. Therefore, S equal to plus or minus of ms equal to plus or minus of mi equal to plus or minus of. Now, on substituting I equal to plus of, on substituting in this expression, E of equal to minus Gn mu n B naught 1 by 2, and on substituting I equal to minus 1 by 2, then minus plus Gn mu n B naught by 2. Similarly, on substituting S equal to 1 by 2, you will get the energy of the I equal to 1 by 2 state. On substituting S equal to minus 1 by 2, you will get the energy of the ms equal to minus 1 by 2 state. As you see, the energy of the mi equal to 1 by 2 is lower in energy, minus. This is higher in energy, whereas in the case of ESR, it is reverse. E, that is the energy of ms equal to 1 by 2 is higher in energy, whereas the energy of ms equal to minus 1 by 2 is lower in energy because of the negative value. Because of the above interactions, the energy level splits into two levels in the presence of magnetic field, applied magnetic field. In the absence of magnetic field, these two levels are degenerate. In the presence of magnetic field, because of the interactions, they split into two non-degenerate levels. With the increase in magnetic field strength, the energy of splitting increases. The energy of the splitting increases. Similarly for ESR. In the case of ESR, the energy of splitting is very much greater, not up to the scale, because of the Bohr magneton. Bohr magneton is inversely proportional to mass of the electron, here mass of the proton. Because of the high mass of proton, the energy of splitting is lower, whereas in this case, the energy of the mass of the electron is very much smaller. Therefore, mu b value is larger. Mu b value is larger. Therefore, the energy of splitting is also larger. Therefore, delta E from the previous slide, delta E can be calculated from the energy expressions Gn mu n B naught. The energy of separation is given by Ge mu b naught. In the case of NMR, radio frequency radiation is used to affect the transition between the nuclear spin states. Whereas in the case of ESR, microwave is radiation, which are of higher in energy than radio frequency wave radiation, are used to cause the transition between these two energy levels. This we will study about nuclear resonance condition. What is nuclear resonance condition? When the energy of the radio frequency radiation is equal to the energy gap, the transition between the nuclear spin states or electron spin states will occur. It is given by the expression energy gap between the two states is equal to, from the previous slide, Gn mu n B naught, and delta E is equal to h nu. Therefore, h nu equal to Gn mu n B naught. When the frequency of the applied radio frequency radiation matches the energy gap, or the precision frequency of the nuclear magnetic moment about the applied magnetic field, then there will be resonance condition satisfied. Each nuclei has a different nu value. Nu value is different for different nuclei because of each nuclei has got nuclear factor Gn and nuclear magneton. Similarly for ESR also. As we have seen earlier, the resonance frequencies are higher for ESR. That is, microwave radiation is required. Microwave radiation is of higher energy than radio waves. It is because of the gyromagnetic ratio of the electron gamma is 659 times higher than the nuclei. For the same field, for free electron, when it is placed in the magnetic field B0 0.32 Tesla, the resonance frequency is 9.8 gigahertz. Whereas for proton NMR, when the same magnetic field is applied, the resonance frequency for NMR is 14 megahertz. The resonance frequencies are gigahertz is 10 power 9 hertz, whereas megahertz is 10 power 6 hertz. The resonance frequencies are very much higher for ESR because of the large gyromagnetic ratio of electron of small mass. In this slide, we will compare and contrast the NMR and ESR spectroscopy. NMR describes the splitting of nuclear spin states, whereas ESR is concerned with the electron spin states, splitting of electron spin states. NMR is applicable for diamagnetic compounds, whereas ESR is a non-invasive spectroscopy. Both are non-invasive spectroscopic technique because the samples are not destroyed during the NMR ESR measurements. The samples can be reused after the NMR and ESR measurements. NMR active compounds are generally diamagnetic, whereas ESR active compounds are paramagnetic. In NMR, radio frequency waves of lower energy, as we have seen earlier, is required in megahertz, whereas in ESR, the energy of splitting is larger. Therefore, microwave radiation of higher energy is required to cause the transition between the two spin states. In NMR, the relaxation times T1 and T2 are of high value, whereas the relaxation times of electron spin states are very much shorter, 0.1 to 1 microsecond. The relaxation times are extremely short. Therefore, because of this, NMR is usually measured at room temperature because of the high relaxation times 0.1 to 1 second. We will see what are relaxation times further in slides. The EPR is measured at lower temperature because of the fact that the short relaxation time. In NMR, the signals observed measured as absorption signal because of the short relaxation times. Line widths are larger. It will exhibit broad EPR spectrum. Therefore, the ESR signals are measured as the derivative signals. In NMR, the line width is very much lower, whereas in ESR, the line width is larger of 1 gauss because of the short relaxation time. Similarly, the resolution in NMR is very high because of the lower line width, whereas the resolution in NMR is very low because of large line width. However, NMR is very less sensitive. We need 1 millimolar concentration to measure the NMR spectrum. For example, if the sensitivity is lower, then we need large concentration of the sample to measure the NMR spectrum. Whereas in the case of ESR, it is very sensitive. Therefore, even 1 nanomolar is enough to measure the ESR spectrum of your compound. In NMR, the coupling constant is expressed in joules, whereas in ESR, the hyperfine splitting constant is expressed in gauss. The splitting is very much greater the ESR compared to NMR. In NMR, we need different probes to record the spectra of different nuclei. Different probes are required, whereas in the case of ESR, EPR, the resonances of different paramagnetic species can be measured in a single run using the same spectrometer. Whereas we need to change the probe for Proton NMR, C13 NMR. In this case, using the same EPR spectrometer, we can measure the iron EPR spectrum, copper 2 EPR spectra, and vanadium EPR spectra, and other free radical EPR spectra. Let us see what is LARMOR frequency. It is the rotational frequency. It is the rotational frequency of the nuclear magnetic moments. LARMOR frequency is represented by W naught. It is a rotational frequency of the nuclear magnetic moment around an external magnetic field. The LARMOR frequency is directly proportional to the applied magnetic field. With the increase in applied magnetic field strength, the LARMOR frequency increases. Therefore, omega naught equal to gamma B naught, where gamma is the proportionality constant called gyromagnetic ratio or magnetogyric ratio. It is different for different proton, where omega naught is the LARMOR frequency or angular frequency of rotation. In terms of linear frequency, omega naught equal to 2 pi nu, we know from physics. Omega naught equal to, it is the angular frequency, it is the frequency of the linear frequency. There is a relation between angular frequency and the linear frequency. Therefore, on equating these two, gamma B naught equal to 2 pi nu equal to gamma B naught by 2 pi. So what is LARMOR frequency? It is the frequency with which the nuclear magnetic moment precedes around an external magnetic field. In NMR, the nuclear spin states are degenerate in the absence of magnetic field, whereas in the presence of magnetic field, these two levels are split. With the increase in field strength, the energy of splitting increases, as you see here. So at lower field strength, lower radio frequency energy is needed, whereas, for example, at higher field strength, we need RF radiation of higher frequency, of higher energy are required. The advantage of using higher applied field strength is that the spectrum is more resolved at higher frequency, higher radio wave frequency, and higher field strength, whereas low resolution NMR is obtained at lower radio wave frequency and lower magnetic field strength. Here we will study about the NMR instrumentation. Based on the NMR resonance condition, h nu equal to Gn mu n V naught, the NMR spectrum can be obtained by two methods, either by varying V naught, keeping nu constant, or by varying nu and B naught as constant. In this case, the magnetic field is varied by keeping the frequency constant. In most of the NMR instrument, the magnetic field strength is varied by keeping the nu constant fixed. Here I have shown the schematic diagram of the NMR spectrometer. What are the components present in it? What are the role of each component? For example, in this case, you have sample holder. It is spinning so that to generate homogeneous magnetic field, uniform magnetic field, that is very important. And it has magnet, electromagnet, yes, north pole, south pole, electromagnet, and sweep coil and sweep generator is used to sweep the magnetic field by varying the magnetic field. Radio frequency transmitter is used to produce radio frequency waves, radiation of frequency nu. It is transmitted to the sample perpendicular to the magnetic field, and the radio frequency receiver is the detector. Using the detector, the radio frequency is received and the signal is amplified to get the NMR spectrum as shown here. What are the important parameters obtained from their NMR spectra or ESR spectra? There are three important parameters obtained from their spectra. They are chemical shift in the case of NMR, whereas in the case of ESR, G values. We'll see everything in future in further slides. Spin-spin coupling constant, J value. Hyperfine splitting A, it is expressed in gauss, it is expressed in hertz. Yes, in comparison table, we'll see further. And the intensity of the peak, intensity gives the, for example, gives the number of types of protons. For example, methylene proton. And the intensity also gives the concentration of the sample. The area under the curve will give the concentration of the sample. So ESR can be used as an analytical tool. NMR and ESR can be used as an analytical tool. As I said in the previous slide, what is chemical shift? It is represented by delta. We'll see now, if you consider a bare proton, there will be no shielding. There will be no shielding by electron. There will be no shielding by other nuclei. Therefore, the magnetic field by the bare proton is equal to B naught. Whereas in the case of proton in a compound or in a molecule, the magnetic field felt by the proton in a compound is less than the actual applied magnetic field. The applied magnetic field is B naught. Therefore, B equal to B naught minus BE, where BE is this shielding field due to the other nuclei and electrons present in the compound. Therefore, the magnetic field felt by the proton in the compound is less than the applied magnetic field. Is subtracted, shielding field is subtracted, or equal to B naught minus sigma B naught. Sigma B naught, that is BE equal to sigma B naught, where sigma is called a shielding constant. It is different for different types of protons because of the different shielding. For example, we have earlier seen the frequency, the NMR frequency for this is a reference compound, gamma BR for reference compound BR divided by 2 pi, and this is the formula relation between the NMR frequency and the applied magnetic field strength B. So in the case of reference compound BR, the field felt by the nuclei in the reference compound. This is a compound, the resonance frequency of the compound nuclei, and BC is the magnetic field felt by the nuclei in the compound. Therefore, chemical shift is defined as nu C minus nu R divided by nu R. Nu C minus nu R divided by nu R into 10 power 6, that is in parts per ppm, because the nu C minus nu R value is very, very less. It is multiplied by 10 power 6. Here we will see what is NMR reference compound. In general, tetramethylsilane TMS is used as the NMR reference compound. It is used to calculate the chemical shift of different proton, different nuclei by using the formula, since we need to know nu R, the resonance frequency of the reference compound. In this tetramethylsilane, why this is used as a reference compound? What are the important characteristics of this compound? Because all the 12 protons are chemically and magnetically equivalent, therefore it gives single signal for these 12 protons with the intense signal. The intensity is very, very high, so it can be compared with the other compounds, and it is very high shielded. Why the methyl protons are very high shielded? Because silicon is more electropositive than carbon. Therefore, silicon donates the electron more electropositive. Therefore, it donates electron to the methyl protons. Therefore, because of the large electron density, the methylene protons are highly shielded. Further, the advantage of using this tetramethylsilane is that its boiling point is very, very low, and also it is very inert. Because the boiling point is very low, it can be removed and recovered when it is added along with your sample. The reference compound is added along with your sample. Therefore, because it is inert, it won't react with your sample compound, and also since the boiling point is low, it can be removed and the compound can be recovered. Here in this, we will see what is low resolution NMR. In the low resolution NMR, the spin-spin coupling constant is not resolved. There will be no spin-spin splitting. For example, methanol. In the case of methanol, there are two types of protons. There are two types of protons, OH proton and CH3 proton. This is the TMS reference compound where delta equal to 0 for reference compound, because for reference compound nu r minus nu r, that is therefore it is equal to 0, delta equal to 0 in delta scale. And this is because of oxygen is more electronegative, it attracts electron pair towards itself, therefore it is less shielded. It is less shielded, whereas methyl proton 3.35 occurs at resonance frequency delta value 3.35, shielded compared to OH proton. Here there is no spin-spin splitting. Spin-spin splitting we will see further. There are two protons, therefore there are two signals because of two different chemical values, proton and proton. Okay, and next at 60 megahertz NMR spectrometer. This is 1,2 dichloroethane. Here the two methylene proton 1, methylene proton 2, they are equivalent. They are chemically equivalent and magnetically equivalent. Therefore, you will get only one signal for CH2, these protons with the high intensity, because there are 4 protons. If the number of protons is more, then the height of the signal will be high. Okay, this is the reference compound signal, EMS. With respect to this, the chemical shift value is calculated. Here, this is 1,1 dichloroethane. This is an isomer of this compound. If you look at this, if you look at the structure of this compound, as you see, there are two types of protons. One is methyl proton and another is CH proton. Okay, so this proton couples with these 3 protons. Therefore, it will split into 4 signal, n plus 1. We will see further. Therefore, it is a tetrad quartet signal with the chemical shift value 5.89. For this proton CH3, this corresponds to CH3 proton. It splits into doublet because of spin-spin coupling with these protons with this proton, n plus 1. Therefore, 2 splits into doublet, 1:1 ratio. Different protons in a molecule gives different chemical shift, because the magnetic field felt by the different types of proton will be different. Therefore, the LARMOR frequency is different. Therefore, they will occur at different chemical shift values. Here, I have given the different organic compounds with the different chemical shift values. For example, aliphatic compounds gives chemical shift values in this region. They are highly shielded, whereas acidic compounds, aldehydes, the protons are de-shielded. Therefore, they will occur at higher del values. Those protons which are shielded, they occur near TMS. The TMS, as we have seen earlier, the protons are highly shielded. Therefore, delta value is 0. delta value is higher, that means they are less shielded. Therefore, shielding increases in this order. The different compounds will have different chemical shift values as shown here. Here, what is spin-spin coupling constant? It is represented by J. For example, let us consider a compound AX type. There are two types of protons. A proton with the nuclear magnetic moment mu1 and X proton with the nuclear magnetic moment mu2. Spin-spin coupling occurs due to the coupling between the magnetic moments of A and the magnetic moments of X. What are the characteristics of J value? J value is expressed in hertz. The unit of J value is in hertz. We have seen earlier. What are the important characteristics of J value? J is independent of B naught. With the increase in applied field strength, J value does not increase, whereas delta value will increase. Delta value will increase with the increase in field strength. The spin-spin coupling constant is independent of the applied field. Equivalent nuclei, then equivalent nuclei, for example, two methyl protons. There are 3 protons in methyl group. They are equivalent nuclei. Therefore, there will be no coupling between them. The third important property of spin-spin coupling constant is multiplicity. What is multiplicity? It depends upon the number of neighboring nuclei. For example, for proton, there will be n plus 1 peaks when delta is very much greater than the coupling constant. For example, we'll see here, this is CH3 proton, this is methylene proton, CH2, this is again methylene proton, and this is of type, this is of M type, and this is of A. Let's label this proton as A, CH2 proton as M, and CH2 proton as X. Okay, the chemical shift values, the center delta A for this proton, delta M is the chemical shift value for this proton M, and delta X is the difference between delta Mx is very much greater than the J value. For example, the spin-spin coupling constant is the spin-spin coupling constant. The del Mx, the difference between the chemical shift of M and X, is very much greater than J. In that case, it will give n plus 1 peaks. It follows n plus 1 rule for proton I equal to 1 by 2. The general formula, for example, if it is I equal to 1, I equal to 3 by 2, this n plus 1 rule is not applicable. We need to use this general formula 2ni plus 1 for nuclei with the spin I. For example, for proton I equal to 1 by 2, then if you substitute in this expression I equal to 1 by 2, n plus 1, therefore there will be n plus 1 peaks. Let us consider this example. This proton, CH3 proton, couples with this proton due to spin-spin coupling. This proton does not couple with this proton. We'll see further. Only one bond coupling, 1,3 coupling are appreciable. 1,5, 1,6, 1,7, they are not observed. Those couplings, long bond couplings are not observed. Therefore, CH3 proton couples with the CH2 proton. This is one type of proton, so it couples to the n plus 1. Therefore, CH3 proton occurs as triplet. And CH2. Now let us consider this proton, CH2 proton. This proton C couples with the 2 of methylene protons and 3 of methyl protons. Therefore 5. Therefore N plus 1, 5 plus 1, 6. There will be 6 sextet signal is obtained for this M-type proton. And for this proton, this proton couples with this. Proton couples with this. Therefore, you will get triplet signal for this proton. This is the multiplicity. What is the multiplicity of this proton? Triplet. The multiplicity of this M-type CH2 proton, sextet, because of N plus 1 rule, 5 plus 1. As we have seen in the previous slide, the J coupling is negligible greater than 3 bonds. For example, I have shown here 1 bond coupling. This is 3 bond coupling. 1, 2, 3. This is 3 bond coupling. It is negligible greater than 3 bonds. 1, 4 bond coupling, 5 bond coupling are negligible. However, there is an exception in delocalized aromatic conjugated system because of delocalization. The J coupling is appreciable even beyond 3 bonds, even in the case of delocalized system. The intensities of multiplets are symmetric about the center. For example, the intensities of multiplets are symmetric about the center of the multiplets. The relative intensities of the multiplets, triplet or sextet, is given by the binomial expansion. Binomial expansion A plus B to the power n. We will see in the next slide. The relative intensities of the multiplets in multiplets is given by the binomial expansion formula A plus B whole power to the n. How it is calculated? Now we will see. For n equal to 0, if you substitute n equal to 0 in this expression, then anything to the power 0 equal to 1. Therefore, it is a singlet. For example, TMS in tetramethylsilane, it is observed as a singlet. All the protons are equivalent. Now, if you substitute n equal to 1, then A plus B to the power 1, therefore A plus B. The coefficients of the binomial expansion 1 is to 1. 1 is to 1. For n equal, therefore, for n equal to 0, it is a singlet. It is expressed, it is shown in the form of Pascal triangle. N equal to 0, it is a singlet. N equal to 1, then it is the doublet. For n equal to 2, the expression is a square plus 2ab plus b square. The coefficients of this equation 1 is to 2 is to 1. For n equal to 3, 1 is to 2 is to 1. Similarly, if you put n equal to 3, then a cube plus 3a square b plus 3b square a plus b cube. Therefore, 1 is to 3 is to 3 is to 1. For n equal to 3, it is a quadrat. Multiplet peak is obtained. For n equal to 4, quintet, 5, and n equal to 5, n plus 1. Therefore, 6 lines or 6 peaks are obtained, sextet. So, using the binomial expansion and their coefficients, the intensities of the multiplets, are obtained. For example, for n equal to 1 singlet and n equal to 1 doublet and n equal to 2, this addition of 1 plus 1, 2, and similarly 1 plus 2. 1 plus 2 gives 3. 1 plus 2 plus 1 gives 3. Similarly, 1 plus 3, 4. This is how the Pascal triangle is obtained from the binomial expansion formula. Here, what are chemically and magnetically equivalent nuclei? Chemically equivalent nuclei. Let us consider the example 1,2 dichloroethane. There are two methylene groups, methylene protons. They are identified and they are identical, chemically identical as well as chemically equivalent. And therefore they have same delta value, chemical shift, the same environment, chemical environment. Now we'll see what are magnetically equivalent protons, magnetically equivalent nuclei. In this case, both have same chemical shift. Both the protons have same chemical shift and also J coupling constant. Here they have only same delta value. Here the two nuclei have same chemical shift value and also coupling constant values. For example, in this molecule, the protons sees this fluorine and sees hydrogen. These are chemically equivalent. They have same chemical shift values, but they are magnetically inequivalent. They have different coupling constant values. Let us see the types of spin-spin splitting. There are three types of spin-spin splitting. Zero order splitting. There is J equal to 0. There is no splitting at all. First order splitting and second order or higher order splitting. Okay, now let us see zero order splitting. For a system, AB system, there are two types of protons, A and B. They are different protons. They have different chemical shift values. You see there are two chemical shift values. There are two protons. But they are not coupled. J equal to 0. Therefore, they have singlet signal. Singlet signal for A proton and singlet signal for B proton. Okay, now let us see first order splitting. What is first order splitting? In the case of first order splitting, the delta, actually it is from delta del value is from here to here, is very much greater than the J value, very much greater than the, that is del delta by J is greater than 8, then it obeys first order splitting, n plus 1 rule. Proton is coupled, A proton is coupled to B proton, therefore doublet signal appears. Similarly, B proton couples with A proton, therefore you will get a doublet for B proton, similar to A proton, and the coupling constant is given by here, del delta by J greater than 8. In this case, a first order splitting is obtained. It obeys n plus 1 rule. Let us now see what is second order or higher order splitting. When del delta by J is less than 8, that is J value is greater. In this case, J value is greater than del delta. Here, del delta value is greater than J value. Here you see this in this case, J value is greater than del delta. Is del delta by J less than 8. In that case, it does not obey the n plus 1 rule. This we will study about pulse NMR. It is also Fourier transform in NMR. All recent NMR instruments are based on pulsed or FT NMR. Let us see now. It is very easy to understand. In continuous wave NMR, it is the old version, and RF radiation is used to affect, a radio frequency radiation is used to affect the nuclear spin transitions. Similarly, in EPR, microwave radiation is used to cause the electron spin transitions from ms minus off to ms plus off. We have studied earlier. Here, RF radio frequency radiation is used in pulse NMR. The radio frequency radiation is used in the form of short, quick pulse. Flash pulse is nothing but a flash of RF radiation. The principles of pulsed NMR and EPR are also very similar. In EPR, microwave radiation pulse is used, whereas in NMR, radio frequency radiation pulse is used. The advantage of NMR is that, the advantage of pulsed NMR is that NMR measurements is completed in seconds, less than seconds, whereas in the case of continuous wave NMR spectrometer, in older version, the time, it is time consuming. We'll see further. As I explained earlier, the continuous wave NMR, it is the old version of NMR instrument. It is time consuming. We need to take several scans. It will take long time for recording, measuring NMR spectra for a single compound. If the intensity is very low, then we need to carry out several scans. Whereas in modern pulse NMR, the sample is excited by a single multiple pulses of strong radio frequency wave of range of frequencies. Then the free induction decay is picked up on a receiver. We'll see the NMR measurement is completed in seconds. This is very important. It is time consuming, the continuous wave NMR, whereas pulse NMR, the scanning, the measurement is completed in a few seconds because we use NMR radio wave pulse of range of frequencies. We'll see the principles of it in the slide. To understand the pulse NMR or pulse EPR, we need to know what is magnetization, what is net magnetization. Let us consider electron spins, either in clockwise spin or anti-clockwise spin. They are degenerate in the absence of magnetic field. They are all randomly oriented in the absence of magnetic field. When in the presence of magnetic field, V0, these electron spins or nuclear spins are oriented. For example, Mi equal to plus of is oriented in the direction of the field. They are lower in energy. Mi equal to plus of is lower in energy. Therefore, it is more populated, more number of spins in the ground state. It is the anti-clockwise spin, Mi equal to minus of. It is the excited state. The number of spins with Mi equal to minus 1/2 is less. The population is higher in the ground state. Therefore, on subtracting, we will get the net magnetization. Overall magnetization is in the Z direction. At equilibrium, the overall net magnetization M0 is in the Z direction. The net magnetization is shown here. The net magnetization as shown here, the previous slide here. Okay, it is in the Z direction. It is in the Z direction. When you apply a 90-degree pulse, that is pi/2 pulse. That is when you apply rotating magnetic field, radio frequency field, perpendicular to the perpendicular to the z-axis, that is through x-axis, it is tilted. The magnetic, when you apply the pulse, radio frequency oscillating magnetic field, it is tilted along minus y-axis. This is plus y-axis, it is tilted along. Therefore, the two levels are equally populated. The two levels are, when you applying the 90-degree pulse, the two energy states are equally populated, they are saturated. Now, when you apply 180-degree pulse, pi pulse, the net magnetization is tilted opposite, that is plus z-axis to minus z-axis. In this case, there is a population inversion. You see, this is thermal equilibrium. The net magnetization is along the z-axis. On applying 180-degree pulse, the magnetization is tilted opposite to plus z. It is in the minus z-axis, minus m0. There is a population inversion. Now, what is pulse angle? This formula is very important, asked in CIR and gate problems were asked based on this. What is pulse angle? This is the angle through which the net magnetization is tilted from the z-axis. For example, 90-degree pulse. This is 90-degree pulse. And this is 180-degree pulse. Theta equal to 180-degree pulse. Theta is radians. It is directly proportional to the rotating, oscillating radio frequency field, magnetic field. It is applied along the x-axis. It is the pulse. It is the oscillating, rotating magnetic radio frequency pulse. V1, it will be given. And what is TP? TP is the length of the time of the pulse applied. How long the pulse is applied. For example, if you apply for a long time, then it will be tilted to minus z-axis. If the length of the time of the pulse is very less, then it will be tilted by a 20-degree, 10-degree, etc. Therefore, the pulse angle depends on the applied radio frequency pulse and magnetic field, and also on the length of the time of the pulse applied. What is population inversion? On applying 180-degree pulse, pi pulse, when the pulse angle is 180 degree, the magnetization, the net magnetization is tilted from plus z to minus z-axis. At that time, the population of excited state and ground state are reversed. It is called population inversion. Whereas when you apply pi by 2 pulse, 90-degree pulse, the energy levels are saturated. There will be no signal. Here we will see there are two important phenomena in pulse NMR or pulse EPR: free induction decay, FID, and spin echo. These are all very important in ESR pulse NMR spectroscopy or pulse EPR spectroscopy. This is again a very simple, if you understand pi by 2 pulse. For example, when you give pi by 2 RF radio frequency pulse, okay, what will happen? I have shown here pi by 2, and the detector, when your eye is in the minus y-axis, okay, now the magnetization is very high. As you see, the magnetization is initially very high in the detector. Okay, so it is very high. After some time, after with increasing time, the magnetization, the individual magnetization fan out. Therefore, the intensity decreases. The intensity of the FID decreases, and finally, it will reach the equilibrium net magnetization. It will go to Z direction. Therefore, the FID signal, free induction signal, is decreasing with respect to time because the net magnetization uh, along minus y-axis undergoes precision and it fans out, therefore it decreases. Now let us see, once after pi by 2 pulse, now after it comes back to equilibrium, thermal equilibrium position, net magnetization is along the Z direction. The pi pulse is now applied. The pi pulse is now applied, as you see here. Okay. Now, the when you observe along minus y-axis, there will be no magnetization because the magnetization is now along minus z-axis. There is no magnetization along minus y-axis. Therefore, it is 0. And with increasing time, the magnetization fans out, and therefore the signal increases and then decreases because of this phenomena. This type of signal obtained is called spin echo, and this signal is called free induction decay because the signal is decreasing with respect to. This is the free FID signal along the transverse magnetization my with respect to time, magnetization along the y-axis, it decreases with the increase in time. We have seen earlier. On Fourier transformation, an absorption signal is obtained. However, if the magnetization is observed, the magnetization, or if the detector is in the x-axis, there will be less signal in the beginning. With the increasing time, the signal decreases because the net magnet, after obtaining pi by 2 pulse, the net magnetization is along the y-axis. The magnetization is intensity is very large. The magnetization along my, after time, it will be decreasing. Here, since it is along the my axis, mx will be 0. With increasing time, it is increasing and then decreasing. On Fourier transformation, dispersion spectrum is obtained. Let us see now what is time domain NMR spectrum or ESR spectrum, frequency domain ESR spectrum, NMR spectrum. Now the magnetization, this is the free induction decay signal, FID signal. This the magnetization along the my axis. A magnetization along Z axis is called longitudinal magnetization. This is a transverse magnetization along x-axis, y-axis. The magnetization along x-axis, y-axis are called transverse magnetization. It decreases with respect to time. This FID signal is called time domain NMR spectrum. This does not give any useful parameters. However, on Fourier transformation, a mathematical process, even our eye does Fourier transformation to give the image we can see, because of Fourier transformation. This is a fundamental mathematics. We don't know, but our eyes are doing this even for uneducated. They don't know. He doesn't know mathematics. On Fourier transformation of FID signal, here you will get one signal because you have only one proton in the compound. Suppose you have two different types of protons or three different types of protons. The FID signal will be, the nature of FID signal will be different. It will be comprising of two different types of protons. We have two different types of protons. Of it. Fourier transformation, you will get two peaks. Means there are two different types of protons with the different chemical shift values. In this, let us see what are relaxation processes and times. So here at equilibrium, the ground state is more populated. The ground state is more populated and the excited states are less populated at particular applied field strength. For example, V0. On irradiation, for example, on applying the pulse on irradiation with the radio frequency oscillating field, now the population is inverted. On irradiation, the excited state is more populated than the ground state. Therefore, there will be no absorption once the excited states are more. There will be absorption of RF radiation as long as there will be population difference between the ground state and excited state. Now, in this state, there will be no NMR absorption, but due to relaxation process, there are two types of relaxation process. We'll see T1, T2, and they come back to the equilibrium levels. There are two types of relaxation process and relaxation times. One is spin lattice longitudinal relaxation process, long time. Spin relaxation process, spin relaxation time is given by spin relaxation time. Now let us see what is spin lattice relaxation. It is represented by T1. The excess energy, as we see, the excess energy is transmitted to the surrounding. In the case of spin lattice relaxation, the excess energy of the spins in the excited state are transferred to the lattice vibrations. Thereby, it comes back to its thermal equilibrium position. Okay. What is T2? T2 is spin relaxation time. It is represented by T2. It occurs due to the direct interaction between the two spin states. For example, one spin interacts with the neighboring spin. As a result of the spin-spin interaction, there will be the energy is transferred from the excess energy is transferred from the excited state to the neighboring spin state. Now we'll see how the relaxation times are measured. They are very, very important because usually T1 is great, spin lattice relaxation time is greater than T2. Okay, spin time. If relaxation is fast, if the relaxation is very fast, NMR spectrum will be very broad. You won't get NMR spectrum. So it is a it is a physical kind of problem. But if the relaxation time is short, for example, in the case of EPR, the relaxation time is very, very short. It is because of that, NMR ESR lines are very broad. We have seen earlier. That's why the derivative signal is measured. We will see further. As a consequence of T1 and T2, the relaxation times are so fast that J coupling also not resolved. Therefore, the structure of the structure could not be elucidated using NMR if T1 and T2 are short. The relaxation. Here, how T2 T2 is nothing but spin relaxation time. How it is obtained? Spin relaxation time is obtained from free index and decay. We have seen it is very simple. We have already seen the free index and decay. It is obtained from FID decay, free index and decay. T2 is a measure of the decay of the transverse magnetization called transverse relaxation time. It is also called spin relaxation time. Is also called T2 is called transverse relaxation time. Transverse because of the transverse relaxation process. For example, here on applying pi by 2 pulse, the magnetization is tilted to, as you see, the magnetization is tilted to x-axis to minus y-axis. Therefore, the magnetization is now in the y, m of y, mz. In the z-axis, it is mz. The net magnetization equilibrium is on applying pi by 2 or a pulse tilted to minus y, transverse magnetization. Now the decay because the individual spins resist fans out, then the magnetization along my, this magnetization along my decreases with respect to time. Okay, with respect to time. Therefore, the magnetization my or mx my magnetization is decreasing. This is the initial magnetization m naught and t equal to 0. Immediately applying the pi by 2 pulse, that is equal to m naught with the increasing time. As you see, the signal decay, that is called free index. And by fitting the curve, using this equation, by fitting the curve, my is known. It is measured by using detector. M0 is known. It is also detector. It can be detected. And e power minus t by t2. T is the time, the magnetization of my. Therefore, by fitting the curve, by knowing the my, m naught, and time, we can calculate the transverse relaxation time or spin relaxation. In this, we'll see how T1 is measured. It is measured spin lattice relaxation time, also called longitudinal relaxation time. It is measured using saturation recovery. It is very simple. What is saturation recovery? If you look at here, on applying 90-degree pulse, the net magnetization is flipped to y-axis. Now, in this case, in saturation recovery, your detector, your eye is along the z-axis. Okay. As you see, in the beginning, there is zero magnetization along z-axis because we have applied pi by 2 pulse. After some time, with respect to time, the magnetization returns. To, and finally, after certain time, it will reach the equilibrium value. The net magnetization will be back to plus z-axis. Therefore, T1 measures the return of the Z component. return of the Z component of the longitudinal magnetization MZ to its equilibrium value. This is called saturation recovery. Okay. Let us see now, as you see here, M0 at this time, immediately after applying the 5/2 pulse, there is no magnetization along Z axis. This is M of Z. And there is no magnetization at time t equal to 0. With the increase in time, there is a return of Z component. The Z component in the individual nuclei returns to the equilibrium position due to the because of and it fans out. It is in the case of saturation recovery, the return of the net magnetization back to the plus Z axis is followed. Now, using by fitting the curve, this curve is obtained because M of Z equal to M of 0, 1 minus e power minus t by t1. In this case, M of Z is measured using this placed along Z axis. Okay. Now M0 is in initial magnetization at equilibrium, and with respect to time, the net magnetization increases. Because of the return of the Z component of the longitudinal, the XY transverse, whereas Z is the longitudinal magnetization component, equilibrium value. By fitting the curve, we can calculate the T1 value by using saturation